All right. So thanks everyone for coming here. We are going to start the tutorial about working with the IBL data. It's going to be an hour-long tutorial. First, we'll have 5 minutes of introduction showing you the kind of experiment we did, the kind of data set that we've collected. Then we'll go into a 20-minute section that will show you how to search for the data set, the data structure, and so on. And then we are going to have a 30-minute section really focused on analysis, where you'll have your hands a little bit dirty. So before we begin, if you have any kind of question, please simply raise your hand, and we'll have staff in the audience to help you and answer your questions. So please don't be shy. We are here to help you. All right. So we are going to work with the Brain-Wide Map International data set. So it's a very large data set. And the aim of the IBL here was to collect neural data at the single cellular resolution throughout the whole mouse brain in mice doing a decision-making task. So in order to achieve the data collection, 12 labs contributed and recorded from 139 mice that performed expertly in 459 behavioral sessions. And because we recorded with multiple neuropixels probe in one session, so up to 2 neuropixels probe, we gathered 699 probe insertions. And after spike sorting, it yielded more than 300,000 units, out of which 45,000 are considered good units, so putative neurons. So you can see that this data set is really large, and here we really want to thank our team, and in particular, the people who collected the data, of which you can see the pictures on the screen. So yeah, thank you for this, and now we get cranking and analyze it. So just to give you some background, this data set was collected using the rig that you see on the left here. So it has a speaker at the top to deliver auditory cues, a screen in the middle where we present visual stimuli. We record the body movement of the animal using different cameras. We also record neural activity using neuropixels probe, so again up to 2 probe for one given session. And the mouse sits on top of a wheel that it can move with its front paw in order to mark a response. So the task that the animal has to do is a visual decision-making task. And to initiate a trial, the mouse has to hold the wheel still for a randomized period of time. Once this is done, a visual stimulus appears on either the left or the right side of the screen, and at the same time, a go cue is played. Then the animal has to turn the wheel in order to move the stimulus on the screen, and if it moves it towards the center, it receives sugar water as a feedback, and if it doesn't, there will be an error tone that is played. Throughout the session, the contrast on a given trial for the visual stimulus can vary from up to 100% down to 0, so where nothing is shown on the screen. And the probability of the visual stimulus to appear either on the left or right of the screen is manipulated in blocks of trials. So here on the bottom, you can see that in the first block, the visual stimulus is more likely to appear on the left, and then it switches to be more likely to appear on the right. And that means that on the 0% contrast trials, the mouse could use the previous history to infer what is the likely side of the visual stimulus. And the switch in block is not indicated to the mouse in any way. So throughout this task, we record different kinds of data. The first kind are behavioral data. So for example, the time at which the stimulus appear on the screen, or the kind of feedback that the mouse received. And we also record the wheel motion throughout the whole session continuously. We record via different cameras the videos for the left, right, or body cameras. And we segment it using deep lab cut, and through that we can track, for example, the pupil, the tongue, the paw, or the beginning of the tail. And we also record the motion energy for the whisker pad and the body. So in one session, we can record with up to 2 neuropixels probe, so this is electrophysiology data. And with that, we can extract either features such as the power spectral density of this raw electrophysiology data, and we also process it using PyKiloSort, which is a spike sorting algorithm, and we can recover the cellular activity of single units. We also record metadata in a database called OpenAlex, and this is really the metadata that you will search for when looking for a specific experiment. So for example, on which mouse an experiment was performed, in which brain region, and so on. So this is what you're going to use for searching data. In order to access the data, we've developed an API called ONE, that stands for Open Your Physiology Environment, and it would enable you to both search, load, and download the data. And we also released the data using Neuro Data Without Border as a format, but for the sake of this tutorial, we are going to stick with ONE. So that's the tutorial of today, and now we will start into looking at the data structure.
Okay, so today's tutorial is going to be interactive, so you should have received an email with both this presentation and also a Colab notebook that you can use to work through the exercises. So if anyone is new to Colab, basically you have these individual cells that you can run, and on the left-hand side there's a play button, and that allows you to execute the cell that's contained within those cells. So for everyone who wants to follow along and do the exercises, I'd like you to go now into that Colab and run the first two cells, so the installation and the configuration. So these are just installing the necessary packages that you'll need, and this takes a little bit of time, so it's good to run this beforehand so that when we get to the first exercise, everything will be downloaded and ready to go. Okay, so as Gael mentioned, ONE is an API we've developed in the IBL that allows you to access our data. So there are three main methods. Search methods that allow you to search for experiments of interest given a specific criteria that you're interested in. List methods that allow you to explore what data are available on an individual session-by-session basis. And load methods that allow you to actually download and access the data itself. So to start using ONE, the first thing is to install it. So it's available as a Python package, so you can just do pip install ONE API. We also encourage you to install another package called IBL lib, which has a number of useful loading and processing functions that we'll use later on in the tutorial. And the very first time that you set up ONE on a new computer, you need to configure it, so just kind of specify which database to connect to and provide some credentials. So basically you just need to copy those three configuration lines, and then you should be good to go on the computer. And then whenever you use it in your code, each time you'll need to import the module and then instantiate an instance to start using it to load data. Okay, so before going into the different methods, it's important to understand how our data is stored. Our data, the data sets shown in blue are stored in different folders. And we have one root folder which we call the session path. So this contains information about the lab, the subject, the date, and the number of the experiment. And this uniquely identifies every single experiment that we have in the IBL. So this session path can also be converted into an experiment ID or an EID. And this is basically a random collection of numbers and letters that uniquely identifies this experiment, and this is how we kind of label our experiments in our metadatabase. So you'll find that you might often need to convert between a session path, so where your data is stored on disk, and this kind of experiment ID. So for that, we have two convenience functions that allow you to convert between the two. So the first is EID to path, so this converts an EID into a session path, and vice versa, path to EID, which converts a session path into an experiment ID. So for each experiment, we can record from up to 2 probe insertions simultaneously, and these correspond to neuropixel insertions. So we also have a unique way of identifying each insertion. So this is either by an EID probe label combination, so probe 00 or probe 01, or alternatively what we call a probe insertion ID, which again is just a random collection of letters and numbers that uniquely identifies every single probe insertion that we have stored in our database. So especially when you're working with electrophysiology data, you'll need to convert between probe insertion IDs and EIDs to be able to load in the correct data that you need. So we again have these useful converters. So given a session EID, you can find the associated probe insertions using this EID to PID method. And vice versa, if you have a probe insertion ID, and you want to find the corresponding session, you can use this PID to EID method. Okay, so we now have the first exercise for you. So if you go into the Colab, you should find a placeholder for each exercise, and there should be already some variables defined. And what we want you to do now is use these converters that we've just introduced to basically turn this session path into an EID, and from that EID find how many probe insertions there are for this session. So I'll give you a couple minutes to now do that, and then we'll come back and go over the solution together. Okay, so hopefully you were able to do that. So if we can go over the solution now together. So basically we define the session path, and what we need to do is recognize that we want to convert this into an experiment ID. So for that we use this path to EID method and pass in the session path. And then once we have the experiment ID, we can then use the EID to PID method to find the associated probe insertions. So you should have found that for this session, the EID is A2E, C, etc., and it has 2 probe insertions associated with it. Okay, so the next important concept is the subfolders in which the datasets are stored. So these are called collections. And so for example, this body camera.times dataset has a collection called ALF. So you'll find in the IBL that we have collections that have raw something something data, and these are basically the raw data that we store. And then there's also one folder called ALF. And the important distinction is that ALF contains all of the processed data. And everything in the ALF folder is synchronized to a common clock. This means that the body camera times and the spikes are all aligned in time, basically. And so you can use this for your analysis to rate, for example, electrophysiology data with behavioral data. It's also important to know that for some sessions, not all datasets are available. So this is due to quality control reasons. And so if, for example, the right camera errored out during the session, in some cases this data won't be available. So this is where the list methods come in useful. So this basically, given a session EID, you're able to list what datasets are available for a given session. So here I introduce you just to one of these methods, so one.list datasets. And what you need to do is pass in an EID, and you can also pass in an extra keyword argument called collection. And what you're returned is a list of all the datasets that are available in that folder. So here you can see we have some wheel and camera datasets that are available in the ALF folder. Another useful method is this one.describe dataset, and this basically allows you to find out more information about a given dataset. So you can pass in a dataset name, and then you'll be printed information about this dataset. We also have a Google document that has a full appendix of all our different datasets, so we've got a link here. So you can also refer to the descriptions there too. Yes?
Can you remind us the different collections besides ALF?
Yeah, so there's like raw ePhys data, raw video data. We also have raw behavioral data, yeah. Okay, so on to another exercise. So this one should be pretty straightforward. I want you to basically do what we've just shown, to use the list datasets method to just explore a little bit what datasets are available for this session in the folder ALF. Okay, so here's the solution to that exercise. So we basically just needed to pass in the EID and use the one.list datasets, and then we can print out, you returned a list of datasets, and you can print those out and then see what is available. So now we're going to take a step back and ask how can we actually find the sessions that we're interested in. So for this, we use the search methods in O&E. So there are 2 search methods. The first is one.search that allows you to find sessions of interest. And the second is one.search insertions that allows you to find probe insertions of interest. So they both work in the same way, where you pass in a keyword value argument. So in the 2 examples here, we pass in the name of a specific subject that we're interested in. And what we returned is either a list of EIDs or a list of PIDs. So here, you can use this one.search terms method to basically list all of the keyword arguments that you can pass in to search over. So there's a big list of different terms that you can use in your search. And here we'll go over 2 specific examples that are probably most useful. So the first is searching by dataset. So here you can specify a specific dataset that you're interested in. So spikes.times, which is a spike sorting output. And we can then pass that in both to find the sessions or the insertions of interest. The second example is searching by brain region. So we can find sessions or insertions that pass through a specific Allen brain region that we're interested in. So in this case, CA1 in the hippocampus. Okay, so on to the third exercise. So for this, I want you to use the search method on the sessions to find all of the sessions that pass through the brain region VPM, and also have this licks.times.mpy dataset, which is an output from the DLC pipeline. So here you'll need to combine two different search terms, and also it's important to note that you need to write query type equals remote, which I won't go into the details now, but if there are questions later, I can describe what that means. Yeah, so go ahead and we'll go over the solution in a bit. Okay, so hopefully you were able to find the number of sessions. So for this, we needed to use the one.search method and basically pass in two keyword arguments, the Atlas acronym, which is the VPM, and also the dataset, which is the licks.times. And then you should have been returned a list of EIDs. And if you can just get the list of them, the length of this list, you find that in total there's 42 sessions in the IBL dataset that match this specific criteria, so that pass through this brain region and have the relevant dataset. Okay, so now we're going on to how you can actually load the data. So once you've used the search methods to find experiments of interest, and then use the list methods to see what data is available for those experiments, you can then actually download and load in the data. So we have three ways to load the data. The first is using these one.load dataset methods. So these allow you to download and load in individual or a list of datasets. So in the first example, we are interested in the clusters.amps dataset, and we use this one.load dataset, pass in an experiment ID, the dataset, and also the folder in which it's contained. We can also pass in a list of datasets, so that's in the second example, and in this case we need to specify a collection per dataset. In the IBL, we also have a concept of objects, where all datasets that are related are grouped together in what we call objects. So for example, all the variables associated with the clusters are grouped together into a clusters object. So we have this one.load object method that allows you to load in all of those datasets in one, and you get returned a dictionary. So in this case, we define our object to be clusters, and we use the one.load object, specify our session, and what we get out is basically a dictionary where each item in the dictionary contains a dataset for that attribute of our object. We've also written some convenience loaders that allow you to load in all of the data for a session, or spike sorting data, and this basically uses ONE in the background, but deals with all of kind of the complications of finding the correct collections, the correct dataset names. So the first is a session loader, and I should say that to use these functions, you will need to install IBL lib, which was that extra package that I mentioned earlier. So the first is a session loader, so this allows you to load in all of the behavioral data associated with the session. So what you do is pass in an experiment of interest, an ONE instance, and then you can load in the trials data, the wheeled data, or the pose data, which is the DLC output. We also have an equivalent for loading in spike sorting data, so this is called the spike sorting loader, and in this case you need to pass in a probe insertion ID, an ONE instance, and then you can use this load spike sorting method, and this will basically download all of the spike sorting data for that insertion. You get the spikes, the clusters, and also the channel information. Okay, so now we're going to go into some more detailed examples, so I'll pass back over to Gael, who will take you through those.
All right, so now we start the section on more advanced analysis. So we are going to have first an example and then an exercise about loading trials data, and then we'll have an example, an exercise about loading the spike sorting data. So in this first example, we want to load in the trials data for a particular session, and we're going to use the load object method that was just described. We're going to explore the structure of this trial object, and then compute the reaction time for all of the trials in the session, and compute whether there is the difference in reaction time between the trials where the stimulus was presented either on the left or the right side of the screen. So to load in the trials data, we use the ONE load object method with an EID as an argument, and also we want the trials object, and this is what we return. Now we are going to explore it to see what's inside. So first, here we print the keys. So you can see it has many keys that actually are the events that happen in the task. And here are two examples that are highlighted. First, it's the stim on times, which is when the visual stimulus appeared on the screen. And the second is the feedback type, so it's whether the trial was rewarded or not. One thing that you should note is that all of these objects have the same length, and that corresponds to the number of trials that is in the session. And if you're more familiar, you can print this as a data frame where each row now is a trial, and you can see the values for all of these variables across all of the trials. So if we take, for example, the second row here, it's trial number 1, you can see that the contrast left has a value of 0.25. That means 25%, and that also means that the stimulus was presented on the left side. So if we want now to compute the reaction time for each trial in the session, we can use these different variables. For the sake of this example, we are going to compute the reaction time as the time difference between when the visual stimulus appeared on the screen, so that's the stim on times, and the moment that we detected a response, so that's when the stimulus was either registered to the center or outside of the screen, and that's the response time here. So because the trials object has a length of the number of trials, we can just simply subtract the two. So that's our reaction time for all of the trials. And now, because we want to compute whether there is a difference in reaction time depending on trials where the stimulus was presented left or right, we have to find the trial indices at which the stimulus was presented left or right. And so here we use the contrast left and the contrast right variables, and we find the indices by finding where they are not nans. And then using these two indices, we can index our reaction time variable that we had just created before. And if we do an average, we can see that the average reaction time was basically doubled when the stimulus was presented on the left compared to the right. All right, so now we have an exercise for you that is very similar in structure. So first, we would like you to load in the trials data for the session EID you see here and compute the difference in reaction time between now correct and incorrect trials. And for the sake of this exercise, we want you to define the reaction time as the difference between the first movement onset that's detected on the wheel and the stimulus onset. And in order to know which trial was correct or incorrect, you will have to use the feedback type variable. It can have three values, 1, -1, or 0. And here we want you to focus on the trials where it's either correct or incorrect, so it's whether it's 1 or -1. So I leave you a minute to do this. Okay, we are now going to go through the solutions together. So first, we are loading the trials data using the ONE load object method, passing in the EID and the trials as argument. Then we define the reaction time as the difference between the first movement times and the steam on time. Then we have to find the indices of the trial where the feedback was either 1 or -1, so that's whether it's a correct or incorrect trial. And then we pass in those trial indices into our reaction time variable, and we do an average to get the average reaction time for either correct or incorrect trials. And here you can see that it's more than double for incorrect trials versus correct trials. All right, now we are going to do a similar type of example and exercise, but for spike sorting data. So first we go through the example together. We're going to load in spike sorting data for a single insertion, explore the clusters and spike object. We're going to get spikes for a chosen cluster, load in the trials data as we just did before for the associated session, and compute and plot the firing rate of our cluster of interest around a trial event. So here we load in the spike sorting data using this specialized method function called spike sorting loader. So here we have to define a PID of interest, and we instantiate the spike sorting loader with that PID and also ONE. Then we download and load the data using a specialized function called load spike sorting. So one thing that you have to note here is the spike loader that you get as output of the spike sorting loader is not yet the data. You have to call in this function called load spike sorting in order to get it. And then what you have to do is using this merge clusters function, and what this does is that it brings the information that is contained notably in the channels dataset back into the cluster. So for example, the channels dataset will tell you for each channel on the probe in what region it was. So if you want to then know what cluster was in which brain region, we have this merge cluster function that basically aggregates this data for you and puts it back into the clusters object. All right, so now we are going to explore the clusters and spikes object. First, we start with the cluster. So we print the keys here. So it has several keys, and two that we want you to focus on today are the label and the acronym. So the label is going to tell you whether the cluster is considered good or not. So good meaning a putative unit. And if it's good, it's going to be labeled with the value 1 and not otherwise. And the second key we would like you to focus on today is the acronym. So that's the brain region acronym as per the Allen nomenclature. So for example, CA1 is a region in hippocampus. And what's important to note here is that the clusters object contains all of the clusters recorded in the single insertion. So if you're interested in a good cluster, or if you're interested in a good cluster in a specific region, you have to filter for this using these keys. Now we look at the spike object. So if we print out the keys, there are two that are of interest today here for you. One is the clusters, and the second one is the time. So again, the spike object will contain all of the spikes recorded in the session for all of the clusters. So if you're interested in getting a specific, spikes for a specific cluster, you will have to filter for this, and we're going to show you how to do it on the next slides. So first, to give you a feel, we just print here the times and the clusters for the first 10 spikes in the recording. So you can see that the time are basically linearly increasing. And the clusters is really the index of the cluster of which a very specific spike belongs to. So if you can see here in yellow, these two spikes, they belong to the same cluster, number 129. So if now you want to get the spike for a chosen cluster, you have to do the following. So here in this example, we show you how to get the spikes for the 25th good cluster. So first, to find which are the good clusters, we have to find where the cluster label is equal to 1. And then we simply index it by saying it's the number 25, because we want the 25th good unit. And then we get this cluster index. And so in order then to get the spikes for this specific cluster, we have to find the spike index of that cluster. So we simply take in the cluster ID that we've just defined and say where are the spike clusters equal to this cluster ID. Another thing you want to probably do is to get the brain region for a chosen cluster. So here you just have to use the key acronym and you can pass in the cluster ID that we've just defined above. So for example, the brain region for the cluster number 174 is VPL here. So we use now the spike index we will use then the spike index to get the spike times for this chosen cluster and align it to a trial event of interest. So in order to get the trial's data, we do just as before. We have to use the load object method with a specific EID. And so here to get the EID, we use the converter function that is PID to EID above because we first started out of a PID. Okay, so now we want to compute and plot the firing rate of the given cluster of interest around the trial event. And the trial event that we have of interest here is the stimulus on time. So that's what we define above. And then we are going to use a specialized function called binSpike that is from a library called BrainBox. So I really emphasize here that you should go to the documentation on BrainBox because there are a lot of these helper functions for you to do raster plots and other kinds of analysis. So this is just one example. And what this binSpike function does is that you can define a time before and after your event of interest. So here it's 0.5 seconds before and 1 second after the stim on time in our case. And we want to count the number of spikes within small bins, so 0.05 seconds here, across this time window that we've just defined around our event of interest. So we get what we call a spike raster here, which is the number of spikes counted in all of these bins. And here, because we're interested in displaying this in firing rate, we simply divide this by the bin size. So to just give you a feel of what this looks like, this is the code to plot. I'm not going to go over it, but what you can see is that this raster object has basically a size of the number of trials. So it's 608 in this particular example on the y-axis. And indeed, if you look at the x-axis, you have minus 0.5 seconds before the stimulus onset and 1 second after the stimulus onset. And this particular cluster is inhibited by the stimulus showing on the screen. All right, so now we have a very similar exercise for you. So we want you to find all of the probe insertions that cross the region SCIG and select the first insertion available as your PID. Then you should load in the spike sorting data for this probe insertion, find the clusters that are in SCIG, and we want you to find the good clusters in SCIG, so with label =1, and count how many there are. And then you'll take the first good clusters in SCIG and compute the mean firing rate between the first and the last spike time of that cluster. So this exercise is divided into 3 code cells, and we're going to go through each one by one. So first, the first cell is to find the insertions that are in the brain region, count how many insertions there are, and take the first one available as PID. So I give you 1 minute to do this. All right, so we're going to go through the solution together. So first, to find the insertion, we use the one.search insertion method, and we pass in the atlas acronym argument with our specific brain region of interest. Then we just count how many insertions there are by taking the length of this insertion variable. And so here there is 268 insertion that cross SCIG. And to get our PID, we're just going to take the first one, so it's index 0 of this variable. So then for the second code cell, we want you to use the spike sorting loader to load in the spike sorting data and make sure to merge the cluster's information with that of the channel using the specialized function. We want you to find the good clusters in the brain region of interest and get the cluster ID for the first good cluster. So you have a minute to do this now. Sorry?
The previous slide, did you show it?
All right, we're going to go through the solution together. So first, we use the spike sorting loader, instantiating it with the PID and ONE to get the spike loader, and then we have to use the load spike sorting method and then the merge cluster to get the data sets. Then we want to find the good clusters that are both, good and in the brain region of interest. So here we can query this all at once to get the good cluster indices. So first we use the cluster acronyms equal to the brain acronym of interest, and we also use the clusters label equal to 1. That means that these are good clusters. And so here, if you just take the length of these good cluster indices, you can see that there are 6 good clusters in SCIG for this insertion. And so now we want to get the first good cluster, so we simply take the good cluster index number 0 here. So that's going to be the cluster ID 895. Now we go on to the last code cell, so here we want you to get the index of the spikes for this chosen cluster and find the minimum and maximum spike time for this cluster, and then find the number of spike and compute the firing rate. So you have a minute to do this. All right, we're going to go through the solutions together. So first, to get the index of the spike object, we simply find where the spike clusters are equal to our cluster ID. Then we find the minimum and maximum spike time for this cluster. So we have to use the spikes index that we found and index the spike times. And we find the min and maximum using NumPy. Then we find the number of spikes for the chosen cluster. So here what you have to know is the spike indices are basically zeros and ones, so we can just sum that to get the number of spikes. And then in order to get that in firing rate, we divide it by the time difference between the maximum time and the minimum time. And here we can see that the mean firing rate for this cluster number 895 is 0.49 Hertz. Okay, so that's the end of our hands-on tutorial. Now we are going to switch to more advanced analysis. So I'm going to go through a Colab notebook with you, but you don't have to run any cells. You just have to listen and follow along. So if you want, you can switch to the public notebook that we have linked. But it's not necessary. You can also simply look at the screen. I just would like to make this bigger. Mayo, how can I zoom in with, sorry. Oh yeah, okay. Can you see well? Hopefully it's big enough. All right, so in this tutorial it's going to be a bit more advanced analysis and we are going to go through two example analyses. One is called the encoding and one is called the manifold. And in both of these examples, we are going to revolve our analysis around a variable of interest, which is called the choice. And the choice is the decision the mouse makes to turn the wheel either clockwise or counterclockwise. For the sake of this tutorial, we are going to call this left or right. And so the choice can have either two values, +1 or -1. And the aim of this tutorial is to assess whether we can predict the choice of the animal. So before the animal made its choice, can we see what it's going to do? And if we can, when can we predict it? Is it like a second before it does it or 10 milliseconds before it does it? So the data sets you're going to use is first the wheel, because we want to predict the choice of the animal before it moves the wheel. We need to make sure that the time window we're using is not contaminated by any kind of movement. So we are going to check that the wheel data is indeed flat, if you like, in terms of its speed and position. We're going to use the first movement as an event, because we want to take, for this analysis, a time window that is before this movement. And obviously, we're going to use spike and clusters data because we're interested in single unit responses. So in terms of the questions that these analyses will answer, first we are going to do the encoding analysis. And here the question is, if you were to rely on a single unit to predict what the choice of the animal will be, which one would you choose? And the second analysis, called the manifold analysis, states that if you were to use all of the units in a given brain region, when would you be able to tell whether the animal is going to turn the wheel left or right? So before you start any kind of analysis, we really encourage you to look at the data using this visualization website. You can see, for example, raster plots at a single trial level and the wheel speed associated and the different task events like the stimulus on time and the first movement time. You can also look at the wheel velocity organized by particular trial count. So here it's organized for either left or right turns. So you can see that indeed the wheel movement is very different for these two kinds of trials. And you can also see single unit responses. So here it's a unit that is particularly sensitive to the kind of movement that the animal does. Oops, yeah, we lost the slides. Oh, great, sorry. So I don't know if you saw the images before, but this is just the wheel speed at different kinds of trials. So whether it's the wheel turns left or right. And I was just saying that you have neurons that are particularly tuned to this movement, and the question we are going to ask in this analysis is whether before this first movement onset we see the same kind of tuning. All right, so I'm not going to go through the installation with you. This you can do in your own time, and we're going to go straight to the code initialization and the data selection. So here are all of the packages you would need for this analysis, and you can select a probe insertion out of all of the ones that we've released. So here it's really going down up to 699 insertion. So here we select one probe insertion. Now we convert this PID into a session EID and the probe name to load data. So first here we load the spike sorting data using the spike sorting loader. And we load the spikes, clusters, and channels, and we merge them as we've seen before. Then we restrict our analysis to only good clusters, so with label equals to 1. And we filter the spikes accordingly to get the spikes only for the good clusters. Then we load in the trial data, and this time we use the session loader. And that's because below we also want to load in the wheel data. So the session loader enables us to load both the trials and the wheel data using just one single function. Now we want to remove the trials where we have nan as a value. So the event of interest is here the first movement times, and it's possible to have trials where this variable is nan, so that's when the mouse basically did nothing and did not move the wheel. So we're just filtering the trials to remove these nans, and then we are going to find the trials for which the choice is either left or right, so value -1 or 1. Okay, so now we go into the encoding exercise. So here again what we want to see is whether single units encode the choice of the animal in a time window before the animal even made its choice. So we're going to compute what we call the modulation index, which is the change in firing rate between the trials where the animal turned the wheel left or right. And we're going to assess the significance of this modulation, and here we'll use a function that was used in our paper. Okay, so here we define our time window as 100 milliseconds before the event of interest, and here our event again is the first movement on time. And the first thing we're going to do is to plot the wheel trace for the first few events of interest to check that the wheel indeed is flat. So here this is mostly the code to plot it, and what's important here is that the first movement time is shown with these arrows here at the top, and the window of interest for analysis is this turquoise rectangle, and you can see that indeed the wheel speed and velocity displayed in blue and black here are relatively flat within this period. So we shouldn't have any contamination of movement. So now we're going to compute the spike rate around our event of interest. So here, again, this is just defining our time window, as we've seen above, this turquoise time window. And we get the spike count in this time window. So that's, again, using one of these BrainBox helper function. And then to compute the rate, we simply divide it by the length of this time window in order to have this in hertz. So now to compute the modulation index, it's basically the difference between this spike rate in the trials either when the mouse turned the wheel left or turned the wheel right, divided by the sum of that. And here we compute a p-value to assess whether this is significant. For the detail around this shuffling, please look at our paper. So now we plot this, and what we see, so this modulation index can have a value between -1 and 1. So -1 means it would be strongly in favor of the left trial, and +1 strongly in favor for the right trial. And what you can see in yellow are the cells that are significantly modulated. So some cells can have a very high modulation index, but it's likely that maybe only it happens in one trial, so it kind of biases the value. So what matters is to see actually significance of that. So you have 3 cells here that are mostly in superior colliculus that you can see here as a region on the left that are significantly modulated. One of them is not so modulated, and the other 2 are rather highly modulated. So that means that you can actually predict the choice that the animal is going to make before it even made the movement. That's rather interesting. And what we want to do now using the manifold analysis is to see when can you predict this. Is it a second before the movement onset, or is it just a few milliseconds before? So that's the aim of the manifold analysis, is to see when the neural activity would represent left or right upcoming choice. And the analysis is done the following way. So for each unit, you have to compute the PSTHs either for the left or the right choice trials. And here we're going to use units that are all in one brain region. That's going to be the superior colliculus. As we saw that before, that's where the cells were found to be modulated and significant. So we're going to then stack all of these units PSTHs in a matrix that looks like this. Then we are going to go and do PCA on this matrix. So you'll have two trajectories for either the left or the right trials. And you'll take the difference between these two trajectories in PC space. And in order to find the latency at which you can basically tell these two trajectories apart, that means you can actually differentiate left or right trials, we're going to take a certain percentage of the rise of this distance here. So to give you a feel for all of the different brain regions that we have in this brain-wide map, you can see that, for example, the PRNR region has a very long latency. So that means that before the movement onset, you can predict the choice of the animal, and that's really like long time before, so minus 100 milliseconds before. And the region of interest that we have in this analysis here is the superior colliculus in pink here. So the latency is more around 40 milliseconds before the choice. Okay. So here we do a very simplified version of this analysis. So we are going to take one PID and select all of the units in SCM. So here we simply use the cluster acronym to get to the cells that are in SCM. And here we just print all of the acronyms of all of the units in this specific recording. So you can see some are in PRNR, some are in MRN, and we're interested in all of the clusters in SCM here. So now we want to create this stack PSTH matrix using all of the SCM cells. So we're going to use bins basically to create this PSTH, and here we are going to use a time window before the movement onset of 100 milliseconds. So here for each of the units found in SCM, we want to find the spikes. Then we compute a raster plot and then the PSTH. So here again we have helper functions to do this for you. And then we simply stack the PSTH. So it's really just an NumPy trick. So if we plot them, it would look like this. And you can see, for example, that the unit number 1 for both left and right choices doesn't seem to make a big difference. But for some other units, like the third, for example, the activity is very different when you compare left and right trial. So now we want to generate what we call a state space. So it's using PCA. So we are just really applying basic functions that already exist in Python and take the trajectory in this PC space for both left and right trial. And if we plot them, this is what you get. So you can see that the trajectories are very different for left and right trial. And now the idea is to compute the difference at each of these time points. So it's simply the Euclidean distance between these two trajectories. And you can see that it's basically increasing over time, meaning that it's more likely to differentiate the two kinds of trial over time. So time here is negative because it's the time away from the first movement onset, and obviously it's more likely to know what the animal will do closer to the actual action, which is happening at time 0 here. So here it's rather wobbly, but that's because we used really only 6 or 8 cells. So if you wanted to do this analysis in a more robust way, you would get the SCM cells from other PIDs, and yeah, you could compute a much better average this way. So we are done now with the tutorial. I just want to highlight before we finish that we have sorry, I can't exit. We have other resources and materials in different pages. It's at the bottom of the slides if you can get back to them, not like me. And we have a Neurostar forum where you can post any questions, especially questions on analysis. It's really welcome. So please feel free to use those resources as you can. Yeah. Sorry, thanks, Mario. Okay.
Another question? So for some of the variables, you said, for example, if it's clockwise is +1, anti-clockwise is -1, or like the feedback, if it's correct, incorrect. Where is that documented? That's not part of the data itself? Is it on a documentation that's separate?
Yeah, it's separate and it's documented in the document that was mentioned before when you can see all the different kinds of data set, the types of the data set. So here, maybe I'll just show you quickly how it looks like. So it's a document called IBL dataset types. And if we just pick one, I don't know, like the feedback type, maybe, oops. That's where it will be explained. So where the feedback was positive or negative, you have the value like this. Any other questions? Okay, so we welcome any feedback. If you think that there are ways to improve this, please feel free to contact us, and otherwise, happy coding.